Hi everyone. As you know, we did a revision class for B9 structures and hydraulics. Today, I provide you the solution for question 1 and question 2. So, in this video, in this short video, I want to explain once more question 1. As you know, question 2 is quite straightforward. I think mostly, as I understand from your friends, we need some maybe more explanation about question 1, but also for who I want to just make a short video for your friends who cannot attend the revision class as well. And so this video, I hope it will be helpful for all of you to just once more to have a repetition of the questions. Maybe you miss some part, and then in this video will help you for better understanding. So let me start with explaining the questions. The question is about a frame with a span of 6 meters. Let me draw the question one, and let me have a pen, and then we have a frame like this, 6 meter span. Is supported, fixed supported. We have 6 support in the column, and the other column we have hinge in the column. And this structure is like it is not a simple structure, so you may need some more calculations, or you need to use a computer program to calculate the shear forces and moments on the beams. But maybe to avoid this, or especially in non-earthquake regions, we use hinges in the beam. So if you have hinges in the beam, you can consider this beam as a simple beam. So in the joints there will not be any moment. If you have moment at the joints, you need to transfer this moment to the columns as well. But in this case, you will have moment only in the beam, so it will be something like this, the moment diagram. But if you don't have hinges here, your moment diagram will be something like this. So according to the if you have lateral force, the moment diagram will be like this. But if you have vertical loads, your moment diagram will be like this. So but in our case we have hinges here, and let me draw the loads as well. We have loads, distributed load, and this is Q equal to 25 kilonewton per meter, and this loss is a uniform distributed snow load. Since it is snow load, so we can consider this as a live load. And also we have point loads as well, and point loads is machinery. So, and machinery also should be considered as a live load, because it may change always, and the snow also, the amount of loads and the places of loads always change. So we consider this as a as a live load. It's changing, so the amount of the load also may change as well. So if I try to derive the dimensions, the dimensions is total span is 6 meter, and this is 1.5 meter displaced, and this is 3.0 meter, and this one 1.5 meters. So Any other loads? We don't have it. We have 2-point loads, and these loads are given as 40 kilonewton, 40 kilonewton, and 40 kilonewton. So in section A, it says applying appropriate load factors for ultimate limit state determine the design moment and design axial force. So we need to be careful about this, since it says like A, we need design moment is MD, we need to calculate design moment, and we need to calculate like design axial force, let's say is ND in the column. Okay, so this is design. Since it is design, so we need to use load factors as well. So that's why first I'm going to start calculating the loads with load factors. So initially, like we have, let me just remind you the load factors from Eurocodes, what we have. Let me write down once more. Like live load is live load factor is, how much is it? 1.5, 1.50, and dead load is what do you think? It should it be smaller or higher than live load? It should be smaller, because that load is those factors is according to uncertainty. So that load is a more certain value. So that's why Eurocode says you need to consider 135, and those factors may change with different countries. For example, in Turkey, we consider live load as 1.6, and we consider dead load 1.4. So it may change according to where you do design for. So your design is, if it is for London, you will consider those load factors. So, and these are our load factors from Eurocode. Okay, and so let's calculate the dead load and then live load. What kind of dead load we have? Let me have another color. So we have dead load. As I told you, like we have distributed 25 kilonewton per meter, distributed snow load, but this is live load. We have machinery point load. Since it is machinery, this is also live load. So what kind of dead load we have? We have self weight. So what kind of self weight will affect the beam? So this is like the weight of the beam. So dead load, we have beam weight. So we can say WB, and as a like live load, we don't have any other dead load. As a live load, we have let's say we have like Q to snow 25 kilonewton, and then we have plus point load machinery. Okay, so and then it looks like for the dead load we will use 1.35, and for live load we will use like this one 135, and this one 1.5. So we will use it. So let's calculate the beam weight first, and then we know the snow, we know the machinery, but we need to calculate the weight of the beam. So how we are going to calculate the weight of the beam? So we need to know the length of the beam is 6 meters, okay, and the section of the beam, let me draw here. So the wideness of the beam is 250 millimeters, okay, and the height of the beam is actually like 550 millimeters. 500 millimeter is D, plus 50 millimeter is the pry, so this concrete cover, so total height is 550 millimeters. So let me calculate beam weight. So WB equal to, we will have like, let's use the units should be similar, and then that's why I will use the unit as meter. 0.25 meter multiplied by 0.55 multiplied by the length of the beam is 6 meters. Okay, multiply, so I calculate the volume 0.25, 0.55 and 6 meter multiplied by the weight of the unit weight of the concrete, actually reinforced concrete, because it has reinforcement in it. If unit weight of concrete, code says should be unit weight gamma concrete is equal to 24 kilonewton per meter cube. But if you have RC, if you have reinforcement in it, and then you need to consider higher, because reinforcement will make the section heavier. So if we say gamma RC is equal to 25 kilonewton per meter cube. So that's why I will multiply this one to 25. Okay, but since it will be distributed load, so then I can delete the 6 meter, because the result I will divide the result to the 6 meter. Or if I'm not going to delete this one, let's calculate. So 20.6 kilonewton. 20.6 kilonewton. So for the distributed beam weight, like, sorry, distributed one, so it will be 20.6 divided by 6 meters, and then it will be 3.44 kilonewton per meter. Okay, so every meter of the beam is, the weight is 3.44 kilonewton, and the beam itself total is 20.6 kilonewton, is about like 2 tons. So it is normal. So as I calculate the beam weight, I want to just calculate the column weight as well. So the column is, the height of the column is 4 meters. So the section of the column, let me draw the section. I'm going to draw the section of the column to here. Sorry, drawing is not very nice, but my pen is a little bit interesting. So 225 millimeters. So 225 centimeter by 25 centimeters. So I can directly write here column self weight. Column self weight is like 0.25 multiplied by 0.25 multiplied by 4 meters and multiplied by, so this is also reinforced concrete, multiplied by 25 kilonewton per meter. So the load will be, the total weight of the column is like 6.25 kilonewton. 6.25 kilonewton. Okay, so the weight of the column is 6.25 and the weight of the beam is 20.6 kilonewton and the column is 6.25 kilonewton. So I calculate the weight of the column and then with the weight of the beam. So now I am going to calculate like design loads by using the weight of the column and the distributed live load on the column, and then I am going to use the weight of the column to calculate the design axial load at the column. So let me delete this part. So and then so we can continue. Sorry, I think my tablet is not very quite good, so it's caused me very hard times to draw something, but I will try to continue. So let me draw this again, and then now I am going to, as I said, design loads. Design loads. For the design loads, we are going to use load factors. What are the load factors? For the like live load, I am going to use 1.5. For the dead load, I am going to use like 1.35. Okay, so let me take another color, maybe this one. So this one is okay. We don't have black one. Okay, I'm going to use this one. Okay, so distributed design load. Distributed design load. Design load. This one is very thick. I need to just decrease this one. Yeah. Okay. Okay. So I will call it like PD. Now it is very, so I need to increase a little bit. Yeah. Okay, so PD equal to 1.5, 1.15 multiplied by what kind of distributed load I have. I have it here 25 snow load kilonewton per meter. So multiply by 25 and plus any other distributed load. Yeah, I have beam self weight. It is also distributed. How much I calculated? 3.44 kilonewton. 3.44, but multiply by dead load factor is 1.35. 1.35. Okay. So PD is equal to, if we do the calculations, we will find like 42.1. Yes, something happened again. Let me 42.1. Oh, sorry. Yes, 42.1 kilonewton per meter distributed design load. I call it PD. So, but we have point load as well. So design point load. So design point load equal to 1.5. Why? Because it is machinery. Multiplied by 40 kilonewton, and it's equal to 60 kilonewton. So now I understand that I calculate distributed load to be 42.1 kilonewton per meter and point load to be 60 kilonewton. Okay. So by using those values, I am going to calculate the moment and actually the axial load in the design axial load in the column, as I need to calculate the first the loads transferred to the column. For this I need to calculate the support forces of the beam. So these support forces will be like axial load to the column, so transfer it to the column, and then I will add the column weight, and then I will find the design axial load for the column at this point at the bottom of the column. So let me delete this area again. So yeah, let me delete all of them, everything. So since it is like recorded video, you can go back, you can go back always and check it. Let me write here 4 meter. Okay, and now I'm going to consider this beam as a simple beam. So let me delete this part as well because I don't have enough spaces. So I'm going to like drive a simple beam instead of the frame. So and then I have support here. I have two support here, one here. So I can consider this as a simple beam, and then I will put distributed loads here, design load PD. So PD is equal to 42.1 kilonewton per meter, and then I have like 60 kilonewton, 60 and 60 here, machinery 60 kilonewton, and let me drive the dimension as well. So here I have like this one, 1.5, 3 meter, 1.5, 1.5, 3.0 and 1.5. Okay, now so I have critical points. Those are like the support, and yeah, this is the support section. And then I have point load. At point load the forces will change, so I can calculate these points. So if I calculate the value of moment at this point, and then of course in between I can like project it as well. But first, when we before drawing the diagrams like shear force diagram and the moment diagram, so my question is to find the maximum values in the length of the beams. For this, first I need to calculate the support forces. Let's say I have this support. I can call this one A, and then this is the second support, the right support. I can name it as B. So I'm going to calculate A and B. So if you make a moment like with reference to A, you can calculate B. But since we have a symmetry, so this is like this beam is totally symmetric beam. So this can be symmetry center, and then A and B will be equal to each other. Okay, so we can say A equal to B. It will be like total force divided by 2. So total force divided by 2. What we have a total force? We have 260 kilonewton. 2 multiplied by 60 plus, and we have 42.1 kilonewton per meter. Okay, sorry. Multiplied by 6 meter. Okay. So if we calculate it, we will find it A equal to B equal to, so if we like simplify to it, this will be 3. This will be 3, and then 60 plus 3 multiplied by 42.1. This will be equal to 86.4, let's say 4 kilonewton. So this is the support force in support A and support B. So this will be axial load for the column as well. But we can calculate design axial force of the column directly but we need to add the column weight. So design axial load for the column, and D will be equal to 186.4 plus, so what is the column? The weight of the column is 6.25 kilonewtons. So total will be equal to 192.7 kilonewton. Okay, so this is our design axial load. So we calculate design loads, we calculate design axial load, only we need to calculate design moment. But in this video we have time, I just want to like continue try to find the shear diagram and then moment diagram. So let me draw the shear diagrams first. If I consider a line like this, let me, from here I have a line or a little bit up because I need to leave spaces for moment as well, and then change color. Yes, so what is the force in support A? Is 186 kilonewton. So shear force here will be 86.4 kilonewton. So we have this point. Yeah, we have this point. So now and so between this area we have like a distributed load of 42 kilonewton. So if you multiply 42 by 1.5 and then 186 minus 42 multiplied by 1.5, we will calculate, we will get like 123 kilonewton. Okay, 0.3 actually it can be kilonewton. So between these two, as we have distributed load, linear distributed load, and this will be first degree. Sorry, I want to like just, yes, this is 4th degree line. Okay, so let me like highlight the point like this. Here suddenly 60 kilonewton point load I have. So if I extract this 60 kilonewton remain, I will have 63.3 kilonewton. Yes, so between these I have 42.1 distributed load multiplied by 3, and 63 kilonewton minus 3 multiplied by 42 point like distributed to 42.1 kilonewton, and then I will get minus 63.25 or 3. So here this will be minus I have a bad tablets, I think. Yeah, somewhere around here it will be 63.3, and then this will be linear again actually. So I need to I will try to drive, it should be symmetry, something like this, and then here suddenly increase 60 kilonewton, and this will be 123.3, and then here I will have linear increase, and then I will get the same value 164.4, and then I can close the diagram with forces in support B, which is 186.4. So this will be like negative and this is positive. So yes, it should be exactly symmetric, but you know, my driving because of the tablet, I have hard time, so please consider this as a symmetric one. So let me drive the moment as well. So if I draw a line like this, so I have important points. This one, the moment will be 0 at the supports, okay? And then if I calculate the area, this area, trapeze area, 186.4 plus 123.3 divided by 2 multiplied by 1.5. Then I will get a moment value like this, 232.3 kilonewton meters. Okay, so if I multiply the area of this small triangle, and then I will get just in the middle, shear value is 0, and this value will be, sorry, this value will be 270 79.8 kilonewton meters. Okay, and I will have the same value here. What is the same value? 232 kilonewton, and here I will have second degree parabola, and this will be of course positive. Okay, so like I say, this is the moment diagram, and the unit is kilonewton meter, and this one is shear diagram, and the unit is kilonewton. So let me continue. Now the first section is done. But in this section, we know we don't need to derive all the diagrams actually. So we know it is symmetric. So the maximum moment will be in the middle. So another way of calculation, we can have the free body diagrams like this for 3 meters, okay? And then we have distributed load of 42.1 kilonewton, 42.1 kilonewton per meter, and then we have here like 60 kilonewton. Okay, we have this support. As support we have 186.4 kilonewton support load. We are going to calculate the moment at this point in the middle. Okay, if we call this 0, so we can take the moment with reference 0. Okay, so this moment 0 will give us the maximum moment, and so the positive signs can be like this, and then we can calculate it. So from here we have 186. Okay, if this sign is 0, so minus, this will be minus 186.4 multiplied by 3 meters, and then the other will be positive, plus 42 point plus, let's say 60 multiplied by 1.5, and then plus we have 42.1 multiplied by 3 meters, okay, multiplied by 1.5, and then if you do the calculation, you will find from free body diagram, you will find the M0, which is MD 279.8 kilonewton meters. Okay, so which is the same value, this you will get the same values, and this is our MD design value. So we calculate design axial load, and we calculate design moment at in the beam. So now we can go to the section B. So let's check the question. What is the section B? Choose the reinforcement bars for the beam necessary to carry the moment found in part A. Following, the moment is 279.8 kN by the way. Following the recommendation of Eurocode 2, any reinforcement bar has to be placed at the distance with D0 equal to 50 millimeter. Okay, let me delete what we did now, delete all of them, and then we are going to calculate the reinforcement with two different methods. Okay, so if I deleted all of them, I want to delete this one to save some spaces because I need spaces, and then my table, my pen, and then my tablet is not very good actually. So I have a section like this, beam section, and the width of the section is 250 millimeter, and I have steel reinforcement. I don't know, it will be 1 or 2. I will have in the negative region as well, but here I have it. I have this one exactly, and this should be 50 millimeter according to the equations. And the other D, you remember D is 500 millimeters. So actually total height will be 550 millimeters. Okay, so in any RC sections we need to first check the deflections, actually strength distribution. Always we have three equilibrium we can use to calculate the reinforcement or the capacity, moment capacity of the section. So one of them is strain compatibility, and this one is, the first one is this, and this shows the section is plain without deflection. When you load it, so that there will be strain like short gauge in concrete and elongation in steel. So here we have epsilon s, so epsilon s, and we have epsilon c, and in the failure epsilon c is equal to epsilon cu, okay, which is like 0.35% in Eurocode, given in Eurocode. And when steel yields, this epsilon s will be equal to epsilon y. So if we know this distribution, actually we can calculate the neutral axis. What is the neutral axis? We can call it as a x. So this shows the change of this line, the change of the signs of the stresses. So like above this line, neutral axis, concrete is in compression, but below this line concrete is in tension. Okay, so we consider, according to ultimate limit state design, we assume that concrete tension in concrete should be taken as 0. Okay, so there won't be any force like under this neutral axis. Okay, this is neutral axis. Yes, so after that we need to calculate the stresses. Okay, we have stresses in concrete. Okay, compression. How are we going to calculate the stresses? So we will use a stress strain diagram of the concrete, epsilon c and sigma c. So basically, as provided by Eurocode, is something like this. Okay, and after this point is concrete crashed at all. So this point is epsilon co, which is equal to 0.0035, and this point is epsilon co is usually 0.2%, and this is correspond to 0.85 FCD design. So what is FCD? FCD is equal to FCK, characteristic stresses in concrete, FCK divided by safety factors. Safety factors for concrete is 1.5 and for steel is 1.15. Safety factors are also associated with the uncertainties. Uncertainty in concrete is high and safety factor in concrete is high. So, and then okay, we need a diagram, this diagram. So we will just directly like project this diagram to the stress diagram to here. So stress diagram will be similar, should be similar. And here like strains are 0 and stresses is 0, and then as strain increases and stresses increases as well. So this value will be 0.85 FCD, okay, stresses. But this is a like second degree parabola, so it will be difficult to calculate the area of this parabola. Basically for forces, we are going to calculate the forces. Let's check the steel. In steel we have only a point, so here we don't need, just we need one stresses, so sigma s, okay. So according to the strain, epsilon c and sigma s, okay, according to Eurocode is bilinear curve. So after epsilon y, and our stresses will be equal to Fy, directly Fy. So which is good. So it's bilinear. Here like we can consider sigma s equal to epsilon s multiplied by Young modulus Es, okay. But below the after this point, so the stresses always will be Fy. So easily we can consider sigma as Fy directly. But in concrete it is not the case. So now for force equilibrium and moment equilibrium we need to calculate the forces. So what forces I have? I have forces in concrete, Fc. So how I am going to calculate the Fc? I need something like this, a volume of something like this, a shape like this. So I can use like equation integral, okay, integrated, but this will be difficult, and then I need a simple method for this. So which is I can use equivalent length rectangular, okay. I can consider this shape as a rectangular. So and the depth of the length rectangular will be A. So according to the codes, A is given, usually A is given like 0.85x according to the grade of the concrete as well. So but usually is at 0.85. So if so, I can calculate Fc more easily, okay. So Fc will be equal to this value, sorry, let me make it bigger, yeah. So this value multiplied by 0. I don't know if it can fit it here, but let me write it 0.85 FCD multiplied by B multiplied by A, okay. So B is the like white of the beam, like white of the beam section. So this is FC and this is FC, and FS will be in this direction. FS will be equal to AS, area of the steel, which is this one, area of the steel, multiplied by sigma s, okay. So according to ultimate state's limit state design, so usually we need to FC to be like at the crashing points for, but not all of them, not all the section will be subjected to the same strain. The maximum strain we want to this strain at the outer of the section, compression section, will be equal to the failure point of the concrete here, 0.035. And then we want yielding in the steel, because if steel does not yield, we are not going to have a ductile failure. The deflection will be so small. So here for this example, how I am going to check, so how I am going to calculate the area, steel area. First I need to check if the moment is big or small. Can this section can carry this moment, or do I need double reinforcement? Do I need put reinforcement in the compression zone as well? So I need to check. So every section can carry a maximum moment. Why? What is this maximum moment? The moment that so ensure for yielding of the steel. So this moment is very high. If it's quite big for the section, I need to put a lot of reinforcement. So in this case, so I need to put reinforcement in compression site as well. So let me check what will be at the balance point, what will be the moment capacity for the balance moment. So the design moment is MD equal to, let me write down, the design moment is MD 279.8 kilonewton. So if I calculate the balance moment, how I am going to calculate the balance moment? So in the balance section, epsilon will be directly equal to epsilon y, and epsilon c will be equal to epsilon cu, which is 0.0035. So if I know this value, I can calculate x, and then I can calculate a. If I calculate a, I directly can calculate fc. So if I take the moment with reference to fc, the tension steel, so fc multiplied by moment length, which is this one, and this is d minus a over 2. Okay, so this is moment arm, so fc multiplied by d minus a over 2, and then I will calculate the balance moment. Okay, so let's do this. So and compare this balance moment with the design moment. So what is the balance moment? I want to drive again. So the balance moment is let me drive here in the balance moment. So epsilon c will be epsilon y, this will be epsilon y, and this will be epsilon cu. So this is equal to, let's say, 3.5 in 1000. Okay, and this will be equal to I can calculate it, fy. What is fy? F characteristic yielding stress for the steel is given like 500. Okay, so epsilon y fyk divided by gamma s, safety factors, divided by Young modulus. Okay, so and 500 divided by 1.15 divided by 200 gigapascal or 200,000 megapascal. So this is equal to, let me see, equal to 0.0021, 0.00217. Okay, so if I get rid of this these zero values, so I can consider this epsilon y as 2.17 in 1000. Okay, so if this is the case, directly I am going to calculate the x. So I have similar triangles, so I can use this equality, which is directly you can calculate x over epsilon cu equal to epsilon y over d minus x. Okay, from this, if we simplify, we will get x equal to epsilon cu divided by epsilon cu plus epsilon y multiplied by d. So, and if you put epsilon cu as 3.5 and 3.5, and this one is 2.17, and then you can calculate x equal to, and d is 500. Okay, 500, and then x can be calculated as like 0.617 multiplied by 500 by d. Okay, so remember this value. Your code says it shouldn't be like over 0.4, something like this. So I am going to calculate this as well. 308.6 millimeters. So this is x. So from x I can calculate a. A is 0.8 x. This is equal to 246.9 millimeters. Okay. So now I can calculate the balance moment. I am going to delete this part for this one. So I delete it. So from this I can do like take the moment with reference to this tension steel. So the moment will be like this. The moment will be like this. MB will be equal to FC multiplied by moment like lever arm is D minus A over 2. So here 0.85. Okay, what is the concrete grade is 25, but 25 divided by 1.5, which is like material safety factors, and multiplied by 250 millimeters B. Okay, wideness of the sections multiplied by A, I calculated A 269, 246.9, 246.9 multiplied by D minus 500 minus 246 divided by 2. Okay, something like this. So the balance moment will be equal to, I calculated as 329.3 0.3 kilonewton meters. Okay, but what would be the maximum moment? This is the balance moment, so we shouldn't be in the balance point. We should have less reinforcement. So that's why we cannot carry the balance moment. Balance moment is also a high value for our section. So the code says the maximum moment will be M max will be 0.8 MB. Okay, so in this case M max will be 0.8 multiplied by like 229.3, and then we will get 263.4 kilonewton meter. Okay, what was the design moment? Our design moment is 279, as you remember, and this value maximum moment is smaller than design moment MD. This is equal to 279. Let me see. yeah, 279.8 kilonewton meter. Okay, so it looks like our design moment is quite high. So if we try to carry this moment only with tension reinforcement, and then what will happen? So ductile brittle failure will happen. So that's why we need to put, we cannot carry these forces. We can carry the maximum forces 263. So there will be a difference between here. So delta moment, I call it delta M. So delta M will be 279.8 minus 263.4. Okay, so this value I need to carry this small amount with reinforcement I will put in the compression region. But before this, I want to show you the second method of calculation of balance moment. Okay, maximum moment, sorry. This is an equations directly given as a simplified method in the Eurocode. So which is like, I call second method. I call it second method. What will be second method is x will be, it says like x will be 0. Maximum 45D. Okay, so and then beta it will be 0.40, and then according those, so these two value will ensure under reinforced section for a ductile behavior. So from this we can calculate the maximum moment ultimate equal to Fc multiplied by D minus beta x. Okay, so and then Fc, what will be the Fc? Mo equal to 0.453 multiplied by FCK 25 and B 250 multiplied by like 0.45 D and multiplied by D minus like let's say D minus 0.4 bit beta multiplied by 0.45 D. Okay, so from these equations we can calculate Mu equal to so we call this Mu Sg max, and this is equal to 261.3 kilonewton. Okay, so from equations and then from balance equilibrium we get almost similar results. So now we can say both ways end up with the similar results. So now we are going to to calculate the reinforcement. So let me delete all of these sections to have some spaces. So almost done. Those are the important points I had to mention it. Yeah, I will delete all of them. So let's take a pen. So we have a section like this. Now I know I need to have reinforcement like in the tension and small amount in the compression as well. So I will call this AS and call this AS prime. Okay, AS prime. Yes, my tablet is terrific. So sorry about that, but I am going to change it after this class as soon as possible. So let me drive like here. I will have like Fc, like forces Fc plus, let me say is delta Fc This will come from from extra reinforcement I put in the compression zone. Here I will have Fs max, okay, plus by delta Fs, okay. So basically I am adding forces like two forces in different directions. So the same forces, these forces are like this delta Fs, and this one delta Fs as well, delta Fs, okay. So easily I can calculate the moment can be carried by this. So the lever arm will be d minus d prime, okay. So now let me calculate this moment first. So as you know, we say like md, design moment is bigger than maximum moment, SK max, okay. So delta md is here, delta md we calculate it as what is the difference is 18.5 kilonewton meter, okay. So this moment should be 80.5 kilonewton meter. For this I can calculate delta F's, and from that I can calculate AS prime, okay, AS prime. So this we can call this like axis moment, sorry, axis moment, okay. So yeah, from balance equilibrium of this section of these forces, so 0.78 Fyk multiplied by AS prime and multiplied by like d minus d prime equal to, so it should be equal to axis moment, which is 18.5 kilonewton meter. If I make it as Newton millimeter, so I will put 10/6, okay. So this will be, I don't know this value AS, okay. I'm going to calculate the AS, but D is 500 and D prime is 50 and Fyk is 500, and from here I can calculate AS prime equal to like 94.5 sorry, not kilonewton, millimeters, okay. So according to Eurocode, I think minimum to make a cage of steel reinforcement like this, so we need to each corner at least have one reinforcement, okay, and minimum dimension KB 10 millimeter I think for the beams. So 2 feet 10 millimeters can be used, which is equal to 625 millimeters. So it's higher than this value, so this is okay. We can use 2 10 millimeter bars. So now we can calculate the tensile reinforcement AS. So from the equilibrium, this equilibrium we can calculate it. Let me take another different colors. So 0.87 multiplied by Fyk multiplied by AS and minus 0.87 Fyk, it is in different directions, AS prime minus 0.453 multiplied by Fyk and then multiplied by B multiplied by 0.45 D. This equal to 0. So from here we can say, like, let me have another color, and AS will be equal to AS prime plus 0.234 multiplied by Fc C K multiplied by B multiplied by D divided by Fyk. Okay, Fyk. So this is equal to 94.5 millimeters is like AS prime, and 0.234 multiplied by FCK is 25, 250 multiplied by 500 divided by Fyk 500, and then we can simplify this. So AS will be calculated as like 1000. Sorry, I'm going to write this right here. AS equal to 1557 millimeters square. Okay, so we can consider like here 25 millimeter bar. Okay, so in this case we need 425. Okay, 425 millimeters bars, and this equal to 1962 millimeters square, so which is higher than this value 1557 millimeters square. So now our reinforcement is, we calculate the reinforcement. Now I am going to delete all the area and then draw the sketch, which is important. Only communication between you and labor is your sketch. Your sketch should be correct as well. So let me drive the sketch. So this is the section C. Section C says, sketch the cross section of the beam illustrating the position of the chosen bars. Secondary reinforcement stirrups need not be shown. Okay, stirrup, but we are going to show it, no problem. So we have, so actually yes, this is section C, and we have a section like this. Okay, and then we have stirrup, should be like a rectangular stirrup, okay, with hooks. And then we will have 4 reinforcement here, 4 rebars, 4, this is 4 by 25, and we need to put minimum 2 bars. This will be minimum 10 millimeters, 2 feet 10. Okay, and then the stirrup will be like this. We can show it like this. It can be by, for example, 8, like it can be 100 millimeters diameter, like distance between the stirrups. And longitudinal sections is also good to sketch it. So we have the beam like this, and then we have 4 25 millimeter bars like this, and we have 2 10 millimeters bars, and we have stirrups as well like this. So between these stirrups can be like 100 millimeters it can be. So you need to show all the dimension as well. Like this will be 550 millimeters, and I don't have distance here, so you need to, like this will be 6000 millimeters. Okay, so this is enough. So we have done with the section C. Now I am going to just quickly check the section D as well. I want to finish it, so let me delete this part. Okay, section D. So in section D, what is the like axial force can be carried by the column? This is an max, we can calculate it. So the axial force carried by the concrete will be FCK multiplied by B multiplied by H, plus if we have reinforcement, we will put reinforcement as well, AS multiplied by FYK. Okay, but no, we don't consider reinforcement. Let's take this 0. Let's check the only concrete. So N max will be 0.85 multiplied by 25 multiplied by 250 and 250. H is 250, and total will be 886 kilonewton. Okay, so what was the design axial force in the column is 192.7 kilonewton. So which is like design axial force is quite smaller than the axial load can be carried by the column. So that's what we can say no reinforcement in the column. Reinforcement in the column, we don't need reinforcement in the column because only concrete can carry all the load. So thank you very much. We're done with these questions. I hope it is helpful, and then sorry about my tablet. The pen is not working very well, so that's why I had some little bit hard times, but I hope still it will be helpful for you. If you have any questions, you can write comments below the video, and then I would be happy to answer it. And then I wish all of you a successful exam for this week. Thank you very much.